Thank you all for joining. Today we have with us Laure. She's a professor from NYU. She's a world leader in this climate forum. So we're very grateful that she joined us today. And yeah, this is one of our almost last seminars of this quarter. We're going to have one more next week, so hopefully you'll be around as well. And with that, I'll leave the floor to you.
Super. Thanks a lot. Thanks for inviting me. Very exciting to be here in the fancy new building. So yeah, it's been a while since I gave a talk at UW. Actually, I think it was about 10 years ago. And I see an old friend in the audience, in a different department. So it's great to be back, at UW and also speaking to a bit of a different audience. So as Anna mentioned, I work on basically ocean and climate related topics. So I know it, might not necessarily overlap with what you do, but it's basically fluids. And we do a lot of data driven things, like you do as well. I like to take questions along the way. So I'm okay skipping a bunch of slides if you start interacting with me, right? So don't hesitate. And if at some point I see that you're asking too many things and I want to say something, I'll stop you. All right, good. So this is, of course, again, there's always one person presenting, but it's work being done with a lot of people. So, to give credit where credit is due. So I'm leading a large, collaboration, supported by Schmidt Sciences. There are about 40, scientists coming from, kind of domain expert like myself in ocean, atmosphere, sea ice, climate model developers. So people who actually build big climate models, but also machine learning experts, meaning people who, again, like some of you, develop algorithm to actually learn something from data. And so this is this kind of big, collision of people with different expertise. We've been working together for the past 5 years, trying to actually, accelerate scientific discovery in climate, especially kind of climate modeling and understanding how the climate system works. Recently, we started new collaboration with a nonprofit called Open Athena. So they are software engineers. They are absolutely stellar. So I'll show a couple of examples of new recent development that we've been, working on together. AI2 was, UW based, not too far from here. I'll show some result and NVIDIA as well. So all those collaborations have also expanded the scope of the type of project that we were able to, push forward, especially in terms of scaling, right? So when you start working with large data in problems that are as complex as climate, you also need, right, the right tools and, the right people that can bring the gap between, people like me who do things at very small scale, and people who need to actually scale up on large, infrastructure. Okay, so that's going to be the roadmap. And as I said, feel free to interrupt as we go along if I say something you don't understand or, if you want to interject. I'm going to give you a little bit of an intro, right? What are the big challenges in ocean and climate modeling? And trying to kind of contrast it with weather, right? Which is usually what you see in the news and, what we're familiar with. I pick my phone and I'm going to check what the weather is going to look like in, 5 days. So I'm going to tell you a little bit the difference between weather and climate, again, just to, set the scene, just to, tell you a little bit about this. And then I'm going to pick 2 examples of the role of AI in climate modeling. One of them is what we call hybrid modeling, meaning we're going to keep the physics, the laws of motion, and we're going to add, if you want, on the right-hand side of those laws of motion, something that we learn from data that we could not resolve otherwise. And again, some of you in this room have done beautiful work in this kind of subgrid closure business, both develop algorithm, but also learn new physics, when it relates to fluids problem. And the second approach, you could say, it's almost kind of the black box. How about we learn the whole equation, right? Input, output, everything in between is learned from data. So now you don't keep the physics plus something that is learned from data. We're going to learn the whole trajectory in one go directly from data. I'm going to use the word data a lot, and I don't necessarily mean observations, all right? So it's not necessarily measurements that you go and you capture. Data for me will be either observations or something that is being simulated, okay? So, I've kind of set the scene in some ways, because if I'm in audience with a lot of observationalists, they're like, well, this is not data. So and it's fair, right? So I just wanted to, clear. And I'm going to show 2 examples of this kind of AI autoregressive model where we learn the whole trajectory. One, which is ocean only, and one, a recent one with AI2, that is a coupled ocean sea ice atmosphere. And then I'll give you some, random conclusions of what I'm thinking about right now, where we see the field developing, which has been developed like so quickly in a way I didn't even imagine when we started this. And we're actually trying to see what it might look like over the next few years and the type of problem that we believe are still grand challenges that we still can't solve with the methods that we have. Okay. So as I said, I'm going to give you a little bit of an intro, right? So usually in ocean and climate, what we do is we try to actually simulate how the planet works, right? So the fluids of the ocean, atmosphere, sea ice, and usually what you have is Newton's law, right? Force equals mass time acceleration, and that's the equation we're trying to solve. So, right, so it's going to represent all the forces, rotation of the planet, the motions of the fluids in the ocean, and so on. So the simulation that you see down here is done by one of the labs, right? So one of the big labs in Princeton, GFDL, and they actually have been building climate models for a very long time. The simulation that you see down here actually is almost 10 years old. They're running the full climate system at a resolution of 1/10 of a degree horizontally, meaning you take the equations of motion, you discretize them on boxes, right? And the boxes are going to be 10 kilometer by 10 kilometer, right? And so it's pretty good, by the way. Many climate models were run on resolution of 100 kilometer by 100 kilometers, so relatively large boxes. And then you can simulate things like this, right? So this is sea surface temperature in this big, climate model. So here you see the tropical Pacific, you see waves propagating. This is El Nino, right? This is one of the signature of the largest mode of climate variability. And so those models really are groundbreaking in many respects, right? You basically put all your equations of motions, all the governing laws of physics, thermodynamics, and so on in one computer, and you try to simulate the planet, and you ask a lot of questions of what if. What if we were to change, the amount of carbon dioxide in the atmosphere? What if, the tilt of the planet compare, to the axis of rotation were to change? So this is the kind of simulation that we built and use for. And they've been fantastic. We use them for forecasting, right? So if you want to forecast what will be the next El Nino event, you'll start with some initial condition, and then you will run the simulations forward in time. And, you'll have different models. And of course, different models will give you a different forecast, as you would expect, right? So there's basically sensitivity to initial condition, but also kind of, different dynamics that is embedded in each simulation. So now when it comes to the AI weather revolution, I would call it in some ways, right? So we see that in the news. So you pick any newspaper in the last couple of years, right? So the AI revolution is changing how we predict the weather. AI breakthrough is revolution in weather forecasting, and so on and so forth, right? So it's been kind of incredible. So what people have done, they basically took data. In this case, it's what we call reanalysis. So it's basically observation merged with a simulation. And the machine learned the whole trajectory, right? So there's data for about 50 years or something like this. And they fully machine learned the evolution of the system and then basically created a forecast model for that. ECMWF, which is one of the big, weather forecast, center, has built even its own AI, weather model, even though they've been doing it with traditional numerical weather models for a very, very long time, and they're very successful at it. And if you look at the skill of their forecast, so this is basically, anomaly correlation as a function of forecast day. The red line is their original numerical weather model. And the blue line is the one that is learned from data with basically an AI model, if you want. So the scale is, right, the correlation is larger, so that means you have more skill in your prediction. So this was kind of, pretty incredible that now you can learn from data and you can get forecast for weather, a few days time scale that would beat what traditional numerical weather prediction can do. The number of groups that have created those AI weather model is huge, right? And the skill has improved with time. So this plot that you see here is basically LMSE skill score for Z500. So basically it's, one of the metrics that we use for weather. So, middle of the atmosphere, so on. Time is done here. Each dot is a group building one of those, AI weather models. So learning the full trajectory pretty much from the same data set always. And so started in, just right, so 6-7 years ago. And then the skill keeps improving. 100 is compared to a traditional, the best traditional weather forecast model. So you see that in a few years, basically kind of got as good as the traditional weather forecast model, and then even better in some cases. But there's a little bit of a plateau, you could say. Right now, they're all kind of aggregating in the same place. But nonetheless, for me, it still blows my mind when I see those plots. Of course, one could say, well, but it was learned on model plus observations combined, and it's, in sample, because the weather, you can repeat it a lot, and AI is very good at learning things that repeat itself. But still, yes, all of those things are caveat, but it's kind of groundbreaking, where we are in the AI weather space. And so as I mentioned, right, so there's this kind of forecast problem where you have an initial condition and you get a forecast, but then you can verify that with observations. The climate problem is a bit different. You don't necessarily just want to do a short-term trajectory with a short-term forecast. What you want, as I mentioned, is those what-if type of question. And that's the way we've been building climate models, and that's the way we also like them because, they solve the laws of physics, and I can understand them, and I can trust the output when I change something in them. And so usually what we change is, we change, the rotation of the planet, and we try to understand, how turbulence is going to change and how that will affect weather or mixing in the ocean, or we change, the amount of carbon dioxide that, we might have in the atmosphere over the next 100 years. And then we plot a trajectory of the global mean temperature anomaly over the next 100 years. And we put different scenarios, and for different scenarios, you get different, global mean temperatures, but different models will also give you different answers, right? Because every model, even though they solve the laws of physics, they don't perfectly solve the laws of physics. And so, building models that you could trust in those what-if scenarios that are not in distribution, right? That's kind of, in the machine learning world, it's like the holy grail, right? You want something that is out of distribution, but also that you can trust because you want to learn something about the physics. So big challenge, out of distribution, or if you want the generalization problem, right? And so how can I learn from data, which sometimes I didn't see because I want to look about, I want to think about the future or a different planet or the past when I don't have data to actually trust it. And so I feel like it's one of the big difference between the weather and climate, perspective. So now I want to give you a little bit of, sense of scale. I know some of you, work on fluids, but usually the type of scales that you might work on is very different than the ones in the ocean. So I like this kind of little diagram where it's just show you a little bit of a range. So usually when we think about the ocean, we think about, those kind of large scale currents like the Gulf Stream, the Kuroshio. They transport a large amount of heat and carbon, right? And they are basically, thousands of kilometers horizontally in scale. They take decades to move things around. They'll influence, how much heat the ocean is taking up, how much carbon, how much oxygen, and so on. But if you go down to, over there, I never know, left or right, depending on which side I am, right? So the smallest possible scales are going to be minutes and meters. So that's going to be the scale of mixing that you would consider. And then, you have basically, instabilities in the ocean that are derived from the large scale currents that have scales of 10 to 100 kilometers roughly. And they're important both in driving the large scale currents, but also in driving the mixing. And so you have this spectrum of scale and they all interact with one another. Now imagine we have equations that solve all of this, right? But you have to go from meters and minutes all the way to thousands of kilometers and thousands of years for the ocean to overturn. So even if you have the equation, which again, to some extent, for certain pieces of this physics, we don't have the equation, but that's another story for another day. Even if we had the equation, then I would need to resolve basically, right, a massive amount of scale if I wanted to actually simulate the whole ocean and the whole climate, which the compute that we have today is just impossible, right? So one of the big challenge is being able to resolve those scales, which usually we can't, and we need to do them fast enough so that we're still around to actually look at the output, right? So this is a big challenge. So here's an example, and I'm not picking on that group, by the way. You can pick any other climate modeling group out there. This is roughly the type of compute you would need. If you were running an ocean plus sea ice model at a 1/4 degree resolution, and just to go back to my little diagram, 1/4 degree resolution would mean that first you don't resolve anything here, right? So anything below 25 kilometers you don't resolve. And here, the grid box size will be roughly sitting on that scale. And those instabilities over here that you see, they're super important, again, for storing heat, carbon, oxygen, and setting the way the ocean works. So everything over there is not resolved. One of the big, instabilities is only partially resolved. And you resolve that thing over here, but again, because they all interact with one another, you're missing a big piece of physics. Okay, so if you take about 5,000 CPU cores, you can run the ocean and sea ice with 12 simulated years per day. Yeah, so I see some faces. Yeah, this is computationally expensive, right? If you want the full ocean plus atmosphere plus land and so on, again, 5,000 CPU cores, 16 simulated years per day. Either way, you get about a decade, 2 decades with 5,000 CPU cores if you want to run, again, and it's only a quarter of a degree. So it's just to show you the scale, right? Impossible to go to the meter scale, minutes for thousands of years with the compute that we have. And for reference, I showed the NYU HPC, right? So if I wanted to do a simulation like that, I will take the whole NYU supercomputer, right? That's not going to happen anytime soon. So because we truncate the equation and we can't solve all of them, what about the physics that we're missing, right? So this is this kind of subgrid parameterization problem that we try to understand. And so the way usually we typically do it, right? So we have our partial differential equations, which we solve on a computer. And then we add a term to the equation that will represent all the mixing processes that we can't resolve, right? And traditionally, the way we've done that, and I'm exaggerating a little bit, but not too much, we try to understand the physics, and then we come up with, a simple mathematical expression, some parameters that will fit to data or not, or that will tune just based on what we need. We'll have some forcing, and then we create an output out of it, right? So that's kind of the way we solve simulations in general. It's not just for ocean and climate, but in general, there are some scales you can't resolve. You come up with a mathematical operator that will represent those scales. You add them to your equation, and that's the way we solve the partial differential equation. That makes sense? All right. So that's the way all simulations work. There's no difference with oceans and climate. This is the same deal. So anything that is below 25 kilometers or so, we just come up with a mathematical operator that represents all the scale, all bundled into one for this purpose, and then resolve it. We run the climate simulations, and then what we like to do is compare with observations, right, over the historical period, because we do have some observations. So here's a typical plot that we do in climate, and ocean modeling. We'll compare to sea surface temperature, where we have a lot of measurements, right? We run simulation for, about 100 years. We pick the last 40 years or so where we have enough observations, and we compare what the model is giving us minus the observations, right? So if it's white everywhere, that means bingo, right? Everything is perfect. Of course it's not. Where it's red, it means that the model is too warm compared to the observations. And when it's blue, that means the model is too cold. So I like to pick this region over here, right? So the Gulf Stream. So the Gulf Stream usually in simulation is too warm, and then its extension is too cold. And it's often interpreted and also kind of verified that the models don't transport enough heat from low latitude to high latitude. That means, right, it starts transporting heat from low latitude, but it kind of accumulates along the Gulf Stream itself, but there's not enough that is being transported to the North Atlantic, so then it's too cold compared to the observations. So this lack of, northward heat transport is kind of known. And it's been around, many generations of climate models for many, many years. And you pick any climate model, you'll roughly get the same type of error. Gulf Stream is not strong enough. It's the same for the Kuroshio. So basically the transport is not strong enough. And one of the reasons it's not strong enough is because a lot of the turbulence feeds the currents themselves and actually helps you transport momentum, heat, carbon, oxygen, and so on, right? So the fact that we're not resolving a lot of the scales actually impact the large-scale transport. So that's one of the big issues we have. So what we've been doing was, okay, so rather than actually go to coming up with a simple term mathematical operator, the way we used to for those parameterization, let's try to learn it from data. All right. So this, and I mean, I'm saying that in front of Steve. I'll embarrass him a little bit, but this was inspired by a paper from Steve quite a few years ago, where they were learning the full, partial differential equation, from data, simulated data, and showing that you can actually, learn the equation just from a set of data. So in our case, we said, okay, let's not learn the full equation. Let's just learn this kind of subgrid term. All right, just a scale that you can't resolve, and see if we can come up with a better closure for it. So we took simulated data. We basically kind of filter it. We learn the term as a residual that is not resolved by the full partial differential equation. And then we use a range of methods. Some, deep learning, some, similar to Cindy, but not quite. We use basically symbolic regression, where we actually learn a parsimonious model that will represent the physics. We build some conservation in it. A lot of the physics that we're trying to resolve is actually not an addition of momentum. It's actually a redistribution term. So we learn terms such that there will be the divergence of a flux, meaning you'll only move things around. You can't just add them or remove them, because that's the way turbulence works. Basically, the advection term makes you move things, globally, but it doesn't add it or remove it. So we can build some like math and physics in it, in the way we learn the terms. We, of course, use domain knowledge in, the sets of basis function that we try to learn from. So we use vorticity, shearing, deformation, which are basically kind of key component of how turbulence work. And we learn that equation directly from data. And so for people like me who are trained in this kind of, geophysical fluid dynamics business, now I have an equation and I can actually learn something from it. So to help us understand how, turbulence at that scale influence the large scale, and of course use it as a new subgrid closure in the model. Right? Which usually if you have a full deep learning model, it's pretty difficult to do, right? You got too many parameters. So we're pretty pleased with that. We could do a lot of physics with it. As I mentioned, we built a lot of different kind of models. But what we've done is we took the big climate model, right? So the big ocean plus sea ice model, and then replaced the traditional physics parameterization with ours, right? So now we remove the traditional parameterization, and instead we run the full climate model, only ocean plus sea ice, ocean plus sea ice model with our new closure that was learned with symbolic regression from data and a little bit of physics. Okay, so I'm focusing only on the North Atlantic. So the SST bias, which is what we call the error, right? So it's red along the Gulf Stream and it's cold where it detaches, right? So that was the same plot that I showed you before. Now, the one below is the response. So it's not the full model itself. It's just if you want, the reaction of the model when we put our parameterization. So the reaction of the model overall is that it'll make the Gulf Stream colder and its extension warmer. So now if you sum up those two plots, that will be the error of the model that we got, meaning we reduce the model error by introducing our closure. And reduce it by, 30 to 50% roughly. So I mean, we were able to actually capture a better representation of how turbulence at the, 10 to 100 kilometer scale interact with the large scale flow. And we were able to actually improve the simulation of the ocean, in particular, again, this kind of Gulf Stream extension, by energizing the flow and kind of removing some of the, errors that we used to. So, of course, we're pretty pleased, as you can imagine. This was kind of a big challenge overall, right? This error has been around for, again, decades. It's a pretty tricky one to get, but, it's like playing whack-a-mole when you actually play with climate models. Is we improved the North Atlantic, we made the Southern Ocean 10 times worse, right? So that means the physics in the Southern Ocean is a bit different, so to speak, or that the model was tuned too much to do one thing and not the other. But this is also exciting because it helps us think, okay, how the turbulence in the Southern Ocean different from what's going on in the North Atlantic? So you ask questions in a different way even when you do something wrong. That's me with my positive, aspect right now. Of course, when you see that, it's not great. But, yeah. Sure. Yeah, so that's a great question. So turbulence indeed is not the same everywhere because it depends on a couple of things. So it depends on the rotation. So it's going to depend on the Coriolis parameter, which changes as a function of latitude. And it depends on stratification, which is basically how the density is stacked in the ocean. So it will change a bit, but there is turbulence everywhere. It is more pronounced in those regions, also because the flow is stronger. And so the instabilities derive themselves from the shear of the flow. And there, the shear of the flow is also stronger. So you have a few ingredients that makes it. But it's a very good question. Also, an additional reason where it's there, it's where the interaction between the large scale and the small scale are the strongest. Yeah, because of the shear. Yeah, thanks. Yeah, feel free to interrupt. As I said, I love interruptions.
Inside the symbolic question that you solve, like that, does that give you any insight into climate dynamics?
The physics? Yeah, definitely. It helps us understand a little bit better how the scale of the instabilities interacted with different type of flows. So it helps us definitely understand how momentum and energy exchange across scales in the ocean. For the word interpretability, I'm always a little nervous because people interpret that would always mean different things. So for me, it was more in terms of learning a new piece of physics from the data. Yeah. Yeah. Thanks. Good question. Okay. Great. So we call that a win, a partial win, even though, there's still some errors. But we also felt like there might be more to it. And so we're trying to actually do the same exercise, but now learning again from data, again, simulated data, a closure, but now using neural networks rather than sparse regression. And again, you could ask the question, but why, right? Like you had a partial win. I also didn't mention, but we were very pleased that there is only one parameter in front, which, this is like magical. It scales with resolution. Like, for me, like it was the holy grail. One thing that almost had no dependence, all the dependencies in those kind of, terms that you have here, which are vorticity, deformation, shear, etc. But again, because we saw some errors, we're trying to understand is there something more, that we would need more expressivity in, the data-driven model that we're not capturing. And so that's why we're actually trying to do a network. We use the same type of inputs as before, as when we trained for the subgrid. And again, we also impose that it's the divergence of a stress tensor. So again, we keep, kind of the symmetries and the invariants and so on the way they're supposed to be. So there's a little bit of constraints. And the way we've done it now is that, because turbulence is changing depending on the flow, but it's also changing depending on many other things. We actually built some normalization in it. So in machine learning, usually what you do is, right, so when you want to train a machine learning model is that, you remove the mean and you standardized globally. But in a field like climate, that makes very little sense, right? Because there's a lot of dependence that are not just a global mean and just a regular standardization. So what we've done is we use Buckingham Pi theorem, which in this case, we kind of did it at the same time. You guys done it with, sparse regression. We're doing it for neural networks. So we built Buckingham Pi theorem by understanding what will be the physical dependence of the local turbulence on, important quantities, resolution, large scale flow, and so on and so forth. And what we could show, so this is basically the true subgrid forcing from, again, diagnosed from a model. This is one if you were doing a traditional ANN where you remove the mean and standardize. And this is one where we build a normalization, again, that is based on physics. So now they both look great, right, compared to the truth. Now, if you try to generalize, which is, again, without retraining, that would be the standard one. Sorry, that's the standard one. And that's the one that is normalized. Okay? And so now you can see that the generalization is almost, intact. So by building the right, physics-based normalization, when you learn those kind of, data-driven model, you can, if you want, help collapse the distribution, which is basically what we're trying to do. So then it can generalize to different climate, to different regimes. And so for us, that was also kind of a big way to think about the problem, which continues to be the grand challenge, right? When I learn something from data, I need to be able to actually generalize and do either the distribution. And to do that, you need to rethink how we learn basically conditional probabilities, which is what we're doing from data. So then we're trying to actually learn a normalization so that the shape of the distribution, right, will translate from one regime to the next or from one climate to the next. So that was pretty cool. When we implemented back into the models, again, it was a pretty good success. It worked out. It did better than the sparse regression. And now what we're trying to figure out is what is it that we capture with the neural network that we couldn't with, the simple sparse regression? What are the terms that I couldn't learn, with just the equation discovery? So that's something that we're trying to think about now is what are those additional terms that seems to be helping with the physics and what do they mean? And so that's kind of, telling you the good and the bad. So, again, as I said, we're pretty pleased, right? We take coarse resolution models that have been around for a long time and they will continue to be around for a very long time, even though we keep increasing resolution, but there's still many scales that we won't be able to resolve. We're being able to actually represent better physics in it, but there's still many challenges, right? So sometimes those simulations become numerically unstable. And because you kind of inject certain things and it's hard to actually control their stability. again, we're learning something from data, as I said, but it's still simulated data. So there's a bunch of errors in it, and there are a lot of scales that we don't capture. So I can go on with, a large number of issues with it. But I think the one that for me kind of got to me was this is a very slow process. So learning a subgrid closure, then implementing it in a climate model, and then being able to run it, which you do with fantastic collaborators and things like this, it takes years. Now, of course, today's one of my colleagues, a couple of days ago, showed me a code that they're actually writing just with agents fully. So then, of course, the hope is that development cycle will go faster, but then also you end up with models and you're not exactly sure what happened in there. So everything has pros and cons. I think development cycle will actually go faster, but the verification will probably be the part that takes longer. But nonetheless, for me, I definitely got a little frustrated with it. And I was trying to understand, is it possible that we could get as much success as the AI for weather for ocean and climate? So could I learn the whole trajectory with still that very grand challenge of generalization, which again, it's pretty severe, and see what happens. But most importantly, now we would be able to actually build model from data that would be open to all, right? You don't need a supercomputer, or, you need one GPU to actually run a model without asking help from anyone. And so that's kind of what we were trying to tackle. Both, can we learn something from data, again, end to end? But also, can we make model accessible and democratized, basically ocean and climate modeling, so you don't need to be a climate modeler or an oceanographer to run them. Okay, so that was my little schematics from before. But now, rather than solving a partial differential equation, I'm going to take a big neural network and then learn the input-output relationship directly. Okay, and again, we're going to still take simulated data because we're building tools, right? And to build tools, it's good to verify what you do. And so having the perfect solution underneath is very useful for understanding how we build things. So the big advantage, which I didn't mention as well, right, is if we build those AI emulators, they're going to be a lot cheaper, right? Because again, learning this mapping at the end of the day is going to be a lot cheaper than running with 5,000 CPU cores. So for that, then that means you can explore many mechanisms, which was one of my, goals. But also you can do long simulation. So the ocean takes thousands of years to spin up, and usually climate modeling centers have to wait a very long time before they can even look at a climate simulation, because you need the ocean to actually adjust as you start spinning up. And also you can do a lot of large ensembles, right? If you have a cheap model, then you can explore extreme, you can do data simulation, or anything else you can think of. And as I said before, you don't need to be a climate modeler, a climate scientist to actually use it if you have it. Okay. So we took the output of one of those kind of, climate simulations. So in ocean modeling, usually the equation that you solve will actually be evolving. Yes, sorry. Oh, I didn't realize that. Yeah, absolutely.
So what's the finest you could get for time interval for your forecast? I mean, the finest I found for, my dissertation was like ERA5, and they are hourly, and there is no opinion minute.
That's correct. Yes. So that's a good question. So I always say, of course, the data that you get will almost determine what you can do, but also what you want to do. Right. So I think the question is, do you really need, minute interval when we want to do something that is longer time scale? Would there be more information, or is it okay to actually take bigger slices? So I think a lot of the AI weather model will be 6 hourly, roughly. Here, the bytes that we're going to take are going to be 5 days. Mostly because the ocean, kind of decoration timescale of the ocean. So, it's like peanut butter compared to turbulent flow. It's kind of, it's sluggish. So we're taking bigger chunks for the ocean. Yeah. And so I'm going to talk about this now. Yeah. So the, input output that we're going to use are going to be the variables that are actually resolved by the climate model, right? So when we solve the partial differential equation, so SSH is sea surface height, right? So it's basically the ups and down, of the surface of the ocean. UNV are the horizontal velocity of the ocean. And you see there is no W because actually we don't solve a partial differential equation for W. We get it from conservation, right? So after you have U and V, you basically assume basically incompressibility, and you infer what W will be by just conservation. T, which is ocean temperature, S, salinity, because the ocean is salty, right? So T, S, and pressure usually determines the density of the ocean. Okay, so that's going to be our input-output that we take directly from a climate model that is called OM4 from the same climate modeling center. This model, this ocean model, is forced with a reanalysis product. Again, it's about, wind stress and heat fluxes with, it's a 60-year simulation roughly. What you see down here is global mean temperature of the ocean in that simulation. Okay. So we're starting in the late 50s all the way to present. The black line is again, global mean temperature of that ocean. And you can see, right? So at the start, it cools, mostly because it's adjusting to the new forcing that it has. And then it starts warming as a response to the surface forcing of the atmosphere. Now, the two colors that you see at the end, this is going to be our emulator. So I'm giving you the answer before the end. You can see we have a problem, right? We get a seasonal cycle, but we don't get the trend. Okay. And so I'm going to come back to it. Okay. So that's the data we're going to pick. We're going to do some tricks to it because this is way too much data. If you save all the data that is being spitting out from the model. So we're going to coarse grain it on the 1 degree resolution. We don't do that anymore. I'll show you our latest model that is on the, original grid. But back then we didn't know what to do because we couldn't ingest the data. We took 5-day means. This is also probably a mistake that we took means and not snapshots. Again, I'm telling you everything, by the way. I think that's how science works. You show the things that work, you show the things that don't work. And 19 vertical levels. So here we actually did the regridding in a conservative way. Because again, right, we care about the ocean heat uptake and things like that. So I need to regrid, the ocean in a way that I'm not losing mass or heat or carbon or something. So again, all of that was mostly done to ingest data. Training sets, I can't read that far, but 75 to 2012. Validation, so, as part of our training. And the inference, so the last 8 years of the simulation is not seen by the model, right? And it's only going to be used for testing. So the machine learning model that we use is UNet. It's been used in many papers, right? It's a nice way to actually capture, different type of connections, short and long range. We've tried quite a few of them. We tried, transformers, video transformers. I think we're trying right now, graphs. I mean, we tried quite a few, in all honesty. The performance does not vary all that much. It just depends on how much data you have, right? The more data you give it, the better you're going to go. We have 135 million parameters. So, give it a lot of parameters, you'll learn what you need. It won't necessarily fix the challenges. So just to, at least for our problem. The learning, we do what we call 2 in, 2 out, is we use the previous 2 time step to learn the next 2. So you can think about as learning the rate of change of each one of those variables. So basically like, Newton's law, right? Force equals mass times acceleration. So the acceleration is the rate of change, of the velocities and so on. So we kind of learning the rate of change. So phi will have all the variables that I told you before. Sea surface height, the horizontal velocities, temperature, salinity. And tau is the surface forcing, right? That is imposed. So that's given. This is not learned. So yeah, we have a loss that is going to accumulate over 4 time step of the model, given that we have 5 days mean, right? So we basically are learning. We basically do a mean square error over 4, recurring time step, which is about 20 days, roughly. All right. So we learn the trajectories. There is no conservation of any kind. We do not impose anything here. We just mean square error. There's no physics if you want. Whatever we learn from data, we learn. Whatever we don't, we don't. That's, again, there's pros and cons. Okay. So again, I'm an oceanographer, I think still, so if you showed me the output, I could not tell the difference. So we run, just to make sure we go back, right? So we train on data set over this period, and then we test on the end, right? But we do it for all those variables that you see at the top. We run over 8 years, and I'm going to show you the time mean over 8 years, some of the variability and things like this. So the time mean over 8 years. So, our model is called Samudra, which in Sanskrit means ocean. So over there, we see a cross section in the Atlantic of temperature as a function of depth and latitude. Okay. So basically it's warm at the top. It's cold at the bottom. That's, because most of the forcing is at the top. You have this kind of double bowl shaped. Again, it's part of the dynamics of the ocean. This is the truth on the left. Samudra is on the right. Again, if you show me and you remove the title and you ask me which one is learned as an autoregressive model versus which one is the original one, I couldn't tell you. right? Does a really good job at capturing the mean temperature profile, and it's kind of true on everything. This is the temperature anomaly along the tropical Pacific. So this represents El Nino, right? So basically waves propagating around, the tropical Pacific, changing sea surface height, but also surface temperature. This is our emulator. So depth versus longitude now, right? So we take a cross section in the tropical Pacific. That's the emulator. That's the ground truth. So here I could hint a little at a couple of things. One is a little noisier than the other, right? But still, the wave speed is right. The profile of the waves are right. So it does a really good job overall at capturing, the dynamics of the flow. Now, one of the big things, yeah, sorry. Yeah, very good question. So yeah, I was about to come back to that in a bit, but indeed, right? So we looked first at the surface, and if I just do sea surface temperature, it's really, really good, right? I'll be like, I'll capture 80% of the variance because most of it is surface. But what's below, then it becomes ocean dynamics, right? Because it will depend on getting the stratification right. Now, separating those two is still a nonlinear process, but the fact that the deeper we go within the main thermocline, we still do a good job, even at the bottom of it. Below the thermocline, we don't. Yeah. So another experiment we wanted to do, right, is we want to run those models for a very, very long time. In weather, what they see is that if you continue rolling out after a couple of weeks, the model becomes unstable. Okay? There are multiple reasons for that. I'm not going to go into the detail, but for us, we wanted to figure out, can we run our ocean emulator for hundreds of years, right? Because again, the ocean is supposed to take thousands of years to adjust. So I don't want to, be stuck after 5 years to have a model that has accumulated so much error that I can't run it. So what we do is we took basically a chunk of surface forcing from the atmosphere and we repeated it, right? Because I don't have surface data for thousands of years. So we kind of fake it. We take a chunk of surface atmospheric data, and then we keep repeating it as a repeat forcing, and we roll out our model. Totally stable, right? So it varies, as it should, but it remains stable for hundreds, thousands of years, no problem at all. Now, of course, one of the reasons is that because we impose a surface forcing. So we can't escape too much. It might be driven, but it still doesn't mean that you didn't accumulate error in the interior that makes it nonsense. And it wasn't, right? So there is a good and a bad, trade-off here. We didn't accumulate error in the interior. Of course, we impose something at the surface, so it kind of keeps it in check, but nonetheless. So now that's where we're pretty excited about, right? So 12 simulated years per day is on 5,000 core. Now we have 4,000 simulated years per day on 1A100. Now, of course, we needed to train, right, before, but you train once, right? So now any of you right now, you can go on Hugging Face, grab this, you can run your own ocean model right now if you wanted, right? And so, when I'm done talking, you would actually have an ocean simulation and you have the scripts that you can play with, you can change your forcing, and yeah, you don't need all that CPU cores and you don't need all the retraining. And so for us, that was pretty exciting, right? It's basically 100 times magnitude faster than the traditional model that we do. Now, of course, we needed that data to begin with, right? So just to keep things in perspective. We tried a few other tricks, yeah. 5 days. Yeah, as I said, 5-day means, yeah, in this case, we're doing 5-day snapshots now. Again, for the ocean, in all honesty, doing it faster has very little relevance for the problems that we're trying to capture for, climate. So yeah, this is literally also, every problem depends, the data will depend on the problem you're trying to solve, right? So the data itself, so we have a portion of the data. I mean, it's huge. That's the problem, right? So the one that is coarse grain and average, etc., we have a link to it, but the original one is just that there's nowhere to store it. Basically, we have nowhere to store it. So it's available on our local machines. But yeah, that's usually one of the issues, right? As you probably have learned, when you want to do data-driven modeling, you need the data. And some data sets are gigantic and people don't have a place to put them. Yeah, that's a good question. Yeah. So one thing we were trying to play with was this kind of, out of sample, but still in distribution. So we took the same backbone architecture. And we try to actually compare, if we were to train an emulator on, say pre-industrial, so where CO2 was 200 parts per million, and compare it to a different time in history, which is called the mid-Holocene, right? So there, again, the amount of CO2 is not vastly different, but there are a few, differences, like, the tilt of the, rotation of the planet and so on. So we basically kind of machine learn an emulator out of one, period of time, and we tested it on a different period of time. And between those two periods of time, actually the seasonal cycle is different, right? And we tried to see if our emulator could actually capture this change in seasonal cycle. And it could, right? So this was kind of exciting, but this is not a full generalization problem. Because the PDF, right, of say temperature and so on is not dramatically different between those two historical periods, but it's still out of sample because it didn't see any of that data. So building those tests when we build the emulators are pretty important because you want to see that, again, you can capture those what if scenarios. So you want to push the boundaries of what you can do with it. And so that was kind of a cool one. So with AI2, as I mentioned, we now build a ocean plus atmosphere and kind of a thermodynamic sea ice now to actually reproduce the whole coupled system. They build the atmosphere using Fourier-Newton operator. Now, in there, they do put some conservation to keep the atmosphere to not leak, different properties. But nonetheless, we kind of coupled our two different components, right? We had the ocean, they had the atmosphere. We brought them together. We actually had a climate modeling center, give us data for what we needed over a long run, which was a substantial, work for them and also for us to actually manipulate the data. But it's pretty exciting. Like now we actually can do those things in a very nice and easy way. And again, right? So thousands of times faster than the original model, one GPU. So same thing, the model is available. You can actually play with it if you want to run a full coupled climate model. We can get the variance as well of ENSO and different modes of variability. But one issue that we have is that everything is too muted. The amount of variance is not as big as it is in the original model. And it's the same for the trend. It's not as big as it's supposed to be. So we're capturing certain aspects that are truly part of the physics, but some are not. So we're trying to understand, is it that we're not capturing the right nonlinearities that amplify the variance? Or is it because we're learning on short, time series, mean square error, completely unweighted, that we're missing, some subtle changes that take longer to overcome? So just the ocean circulation, again, I'm an oceanographer. I was pretty pleased that we can reproduce the pattern and, the variance of the large scale overturning circulation in the ocean. But let me kind of spend a few minutes on still the remaining challenges. So, if one of you wants to work on that, you'll have a whole thesis. So one thing, and that drove us crazy for a long time, it's what we call mixed scales. So velocity and temperatures in the ocean vary on different spatial and temporal scales. The velocity is super fast, has much smaller scale than the temperature. There's a smoother and has longer decorrelation time scale. So when we learn our models, our emulators, again, with velocities and temperature, they look pretty good, except when we started looking at maps. When we started looking at maps, we realized that the temperature actually had an imprint of the velocity, had a lot of small scale things that almost look like velocity, as if, the machine learning, learn a combination of those two together. At the end of the day, it's minimizing mean square error. So it still does a good job, but doesn't know how to distinguish between the two. And so we ended up with, again, what we call the imprinting of the fast variables onto the slow one. So just to show you an example, that's the temperature anomaly in the ground truth data. That's the velocity anomaly in the ground truth data. That's our original emulator. So, not quite the same. So if I were to sum up those two, I kind of get that. Again, I'm exaggerating a little bit, but just to show you, they kind of, mixing the scales. This is our new version, where there's a lot less of that, of this imprinting, and it's the same when we do a global mean averages. Two ingredients that we had is we made the, network wider. And so that's been shown in other applications that actually making the network wider rather than deeper actually helps We're still trying to figure out exactly why. There are a couple of, hints in some of the old papers, but we can't quite pin down exactly the reason for it. The second thing is what we call a dynamic class. So what the dynamic class is doing is giving different weights depending on the amount of variance that you have. So I told you about temperature and velocities being different, but also upper ocean versus deep ocean. I'm going back to your point before. So as we go deeper into the ocean, the amount of variance is much smaller, right? Because it doesn't fill the atmosphere. Everything is going on in the ocean is actually kind of muted deep down, takes a long time, variance is tiny. So now you have tiny variance at the bottom of the ocean and high variance at the top. So basically, again, machine learning just learned the top, doesn't know anything about the bottom. And so kind of rescaling based on the amount of variance helped both with the imprinting and I'm not going to say in getting better deeper ocean because it's still not good at all, but less bad, I would say. But this is it's not a great trick, right? Like I have to go and I have a scalar that I have to change all the time depending on the variance. So I mean that there might be like more clever solution for us to think about when we have this kind of very different spatial and temporal scales that we're trying to capture. Because again, right, this is not just weather where you need just a few days of a few variables. We need thousands of years of many variables that vary very differently. So we're getting there. So we have a new version, does better, but I'm not 100% happy with the solution, I would say. Second thing is conservation, right? And I showed you at the very start. So global mean temperature in the original model is in black. Our emulators are like that. They're flat, right? Now, the trend, you see it here nicely because I took all the grid points, right, in the ocean and integrated them together. But look at the magnitude of global mean temperature. This is tiny, right? This is a tiny trend. And at every grid box, that trend is even smaller. So now again, right, we're trying to learn over short-term trajectories where there's a lot of variance and a minuscule trend, which is, again, spatially dependent. So there's nothing, right? There's not enough for the machine learning model to actually learn that small residual. But that tells me it didn't quite get the physics right. And in climate models, usually the way you get all the conservation right is that you build conservation at every grid box. The way you design the algorithm is to be conservative both locally and globally. So we're exploring kind of a new way to build local conservation in our architecture. I'm not going to say we succeeded, but this is work in progress because at the end of the day, we don't want to just get the global mean trend right, which you can do. You can add strong constraints and a lot of groups are doing it, but that doesn't mean that you're going to get it locally as well, right? Because you need things that go into the box being equal to what goes out of the box, right? Both locally and globally. So this is a grand challenge, I would say, right? If you want to build climate emulators, they have to be conservative because we want to do climate, right? And we want to be able to understand what's going on. The memory limitation, I told you before, right? We couldn't ingest all the data. So we've been working with NVIDIA and OpenAthena. They solve all of our problems. So now this is the new version of Samudra on the original grid. So now it's a quarter of a degree. Again, you of course get to see the turbulence. The waves are propagating better. So now you actually, I think we put it online a couple of days ago somewhere on our website. So now you can have actually the higher resolution simulation if you wanted to. A bunch of things that we're thinking about right now is trying to actually learn from many data sets. And so, some of you have asked a question about, the frequency. Some of the observations are very sparse, but, higher frequency. But there's a lot of information in them, right? And some model data is different. So we are building a new architecture in latent space that are actually kind of ingesting and learning from a range of data sets. And now true observations and simulated data, all of them together to actually not just do a forecast, but actually trying to understand if there's something that we don't understand yet about scale interaction in the ocean. We have a new sea ice emulator that published, I think, a couple of weeks ago. So now you can run a full sea ice model if you want to understand how, the polar oceans work. And we have different versions of the atmospheric model as well with transforms. So a lot of tools, I would say some big challenges still remains, right? So I'll skip that one. But, at the end of the day, we'd like to build tools to learn something. I would say we learned a few things, right? But we're not there yet because there's still issues in how we build those tools, right? We want to build them to understand how the climate system works, but they need to respect, a few properties that we don't grasp quite yet. but I think it's also an exciting way, right, to rethink old questions and to ask new ones. And so hopefully, answering some of our outstanding problems that we couldn't solve before, but also kind of exploring new problems we didn't think about. And I was in a talk not too long ago where I saw S&P Global using some of our emulators to kind of, explore climate risks. And so people use those methods now to explore, questions that they have that we don't have. And so I find that pretty exciting that we can open the door to a lot of those, questions, with those methods. And so I'm going to leave it at that and think I have a few more minutes for questions if there are any more. Thank you. Two slides. It doesn't. Yes, very similar. Basically, at the end of the day, we're trying to learn from multiple data sets on multiple tasks, on multiple downstream tasks. So we're not going to be perfect at, each one of them, but we fine tune on others. For us, the grand challenge is, again, right, so some of the data is on a grid, some is not, some is high frequency, some is low frequency. So this is one of the big challenge. Yeah. Yeah. Thanks for the question. Six hours. Yeah, thanks. Yeah, that's a good question. Okay, so there are a few parts to that answer, right? So when we learn, IMSC over a certain amount of time, right, I need to backpropagate, right? So at the end of the day, I want to make sure that I'm capturing the right physics that should be right at short time scale and long time scale, right? And so now if I want to backpropagate with, say, hourly data for 1 month, this is computationally expensive. Now, if I want to do something where I have no information in between, month 1 and month 2, then I can train a model with a 1 month time scale. And we've done some of that. It always depends on the question you want to address, right? So here I showed you, average quantities, but we look at ENSO, for example, where we need a resolution of a few days time step and not monthly. So it always depends on the question you want to address, right? Well, depends, right? If we want to understand how entry changes under climate change, fair enough. If you want to do an understanding of ENSO over its own evolution, then you actually kind of need the wave propagation. That is a few days time scale, right? I mean, a few weeks.
So if you don't mind, can you say that what approach you wanted to take to make it better? Because you're working with autoregressive, which relies heavily on previous
steps. Yeah.
So I want to see if you can just have a model with that works
Fusion.
better with less data, so it's easier to have it, anywhere else servers.
Okay. So, I mean, not happy. I mean, I think that's the state of science, right? That's good. Like, otherwise, what do we do, right? So anyway, so I think the unhappiness is this, right? We still can't get a model that will capture the trends. And I think, that's a big challenge, right? At the end of the day, if I had a forcing, right? If I have a 1 watt per meter square, the ocean should be taking up 1 watt per meter square. There is no leakage. If it doesn't, then that means there is a problem. And we haven't found a solution for it yet. So that's what I mean by, we're not super satisfied. Is it a problem in the data? I mean, there's a trend in the original data and he didn't get it. So it's not just an out of distribution. There is something fundamental that we're not capturing. So that's why I don't think it's just a data problem here. Yeah. Hey, Greg.
That's not the ocean is a lot bigger. And is the wide network giving us much larger bases?
So that's what we think, but now we need to prove it, right? Which is a non-trivial, let's put it this way. But yes, that's what we're thinking. Yep, correct. Yeah. So it's basically a distilled version of GraphCast. I mean, way distilled, as you can imagine. Yeah. So non-conservative, though we have a version now where we're trying to actually build some conservation in there. Yeah. Sure. Sure.
Almost the same thing that we train like for like some amount of years and evaluating the next one and the
Mhm.
next one. Third pattern might become faster.
Yeah, so that's a good question. I showed one thing. We do many things, right? Sometimes we, learn from the 2N period and find in the middle. We do some shuffling as well. We're trying to learn latent space as well. So we're trying a little bit of everything. I would say there's no major improvement in the way we do it right now. I do think moving into latent space might help for generalization, but right now this is just a hope. Yeah. Yeah, it's a good question. Those things are important when you train models, yes. All right. Mm-hmm. So colleagues at Polymathic, for example, in New York are basically learning on, multiphysics or one type of physics to, train on something else. So far, for the applications that we have, we still struggle in finding those simpler models to work, but I'm not saying it wouldn't, right? I think right now we haven't found it. For the subgrid problem, we did find possible translation between simpler to bigger, but not for this type of end-to-end yet, right? Who knows? Thank you very much.